Hey everybody. Today we're talking about how to compute probabilities for continuous random variables using R. R comes with 4 built-in functions for each major continuous probability distribution, including all your favorites, the normal, gamma, chi-squared, and exponential distributions. The format of the commands is the same for every one of those distributions. PDFs start with the letter D, CDFs start with the letter P, inverse CDFs start with the letter Q, and to generate random values, the function will always start with the letter R. The rest of the function name is just a shortened version of the distribution name. Here's a table for the 4 most common distributions that you might need to calculate in. For instance, if you want to do a calculation in the normal distribution, you use dnorm for the density function, pnorm for the CDF, cumulative distribution function, qnorm for the inverse CDF, and rnorm to generate random values. Now, one important warning is that if you're looking at the exponential or gamma distributions, R is going to be parameterized using the parameter lambda, which is the mean number of occurrences per unit time interval or unit interval, rather than theta, which is, I think, generally a little bit more common in theoretical statistics, which represents the mean waiting time between occurrences. The relationship between the two is just a reciprocal relationship. Lambda equals 1 over theta. So translating from one to the other isn't hard. You just have to be aware that you may have to translate. All right, let's do an example. Suppose that we have a random variable x with a gamma distribution with parameters alpha equals 5 and theta equals 15. So it's representing, for instance, the waiting time for 5 occurrences in a Poisson process in which the average time between occurrences is 15 seconds. So here I'm giving you theta. So notice right off the bat that means lambda is 1 over 15. I'd like to do a couple of probability calculations here. I'd like to compute the 50th percentile, the median of this random variable, and then I'd like to generate 1,000 random observations from this distribution. So as usual, I recommend pausing the video, trying this on your own before seeing how I do it. Let's start with those probability calculations. We use p gamma to find the probability that the waiting time is less than a specified value. So if we need the probability that x is greater than 75, we have to do 1 minus the probability that it's less than 75. That is 1 minus p gamma, 75, 5, 1/15. 5 being the parameter alpha, the number of occurrences we're waiting for, 1/15 being the parameter lambda, the average number of occurrences per unit interval. In this case, we get about 44%. Similarly, we can get the probability that x is between 70 and 80 by doing p gamma of 80, 5, 1/15 minus p gamma of 70, 5, 1/15. So same parameter values, we take the probability that x is less than or equal to 80 minus the probability that it's less than or equal to 70. In this case, we get about 11.7%. Okay, let's talk about the median. That's the value of the random variable for which the probability that the random variable is less than that value is equal to 50%. So basically, if you run this probability experiment many times, half the time the results will be less than or equal to that value m. We could do that by guessing and checking with p gamma, just doing it directly, but R has a built-in function, q gamma, that will do this automatically. It's the inverse cumulative distribution function. The syntax is very similar to p gamma, except now instead of feeding it an x value and getting back a probability, now we feed it a probability and get back an x value. So q gamma of 0.50, 5, 1/15, it's about 70.1. Notice, by the way, that we're feeding q gamma a decimal, 0.50, rather than a percentage, 50. So this is the median of this distribution. In words, the waiting time for the 5th occurrence is going to be less than 70.1 seconds, 50% of the time that we run this probability experiment. To generate random values in this distribution, we use the R gamma function. We want 10,000, or rather we want 1,000 values, so we do R gamma of 1,000, 5, 1/15. Notice how the parameters are exactly the same here as in the p gamma and q gamma commands that we did a little bit ago. Same parameters, same order. The first line that you're seeing here, by the way, set seed 123, is resetting the random number generator, so if you run this code, you'll get exactly the same values I do. The first few of those are 33.56, 77.87, and so on. Here's a histogram of all 1,000 values, and you can see the general shape that you would expect from values generated from a gamma distribution. We know that the expected value of the gamma distribution is alpha times theta, so if we do that arithmetic out, we get 75 in this case. If you put your finger on this graph, under this graph at x equals 75, you expect the histogram to balance more or less. Now, we haven't mentioned d gamma in any of these examples, and the reason for that is that d gamma doesn't get used directly in probability calculations of any sort. It's mostly a theoretical construct. Typically, the only time we use d gamma in R is if we need to generate a visualization of the density curve. So here's some sample code to do that, very simple version. I'm not going to talk about it at all, but you can see the gamma distribution, the density function for the gamma distribution that we've been working with pictured here.